Today we'll be working on the following problem. Now with the notation of problem 39, now we define E to be the set of OZ in X at which the sequence F sub n does not converge subuniformly, and F to be the set of OZ in X at which F is not continuous. So now from problem 39, we have proved that F is a subset of E. Now in this problem, we want to show that both E and F are meager. So pause the video if you want to work on this problem by yourself. Okay, let's see how do we prove this. Right, basically from the definition of this converge subuniformly, we want to rewrite this E to be a union or intersection of some basic set. So first, it is sufficient to show that E is meager, right? Because F is a subset of E. If E is meager, F is meager, right? So now we define this set G M K to be the union of n greater or equal than M, and then the set of X for which F sub n of X minus F sub M of X take absolute value is greater than 1 over K for every M and a K. It's an integer, right? So we know this set because this is closely related to the definition of converge subuniformly, right? That's why we construct this, define this set. And then we let G to be the union from K from 1 to infinity, and then the intersection M from 1 to infinity, this closure of G sub MK, the closure of this. So we will see later why we're doing this, right? So now from this definition, first we claim that E is a subset of G. And now later on we'll show like G is meager. And then we show that E is meager, right? So for this, we claim that E is a subset of G. Because for any, let's pick any Z not in G. And which is, this is, we just flipped the union and intersection, right? So K from 1 to infinity, and this union M from 1 to infinity, this the closure of this, and then take the complement, right? So for any of this, so if Z is not in G, now for all epsilon greater than 0, we can choose some K in N such that 1 over K is less than epsilon over 2, right? So clearly this such K exists. And now since Z for any K, right? So this intersection of K from 1 to infinity. So for this particular K, Z must be in the M from 1 to infinity, this MK, the closure, and then take complement, right? So Z must be in here. So then there exists some M greater or equal than 1, right? So because Z is in the union of this, for this m, z must be in the complement of this closure of G, M, K, right? And this which is open, because it is the complement of a closed set. We're taking the closure, right? So now, if you look at this graph here, we have this is space X, and now we have some G M sub K here, and then Z is not there, right? Z is outside of the closure, the complement, or outside of the complement of G sub K, right? So then we can find some delta. This is Z. We can find some delta around this, the neighborhood, right? So we shall put that's, there exists some delta greater than 0, such that this set, this set, the set of all y, where we have the distance of y of z is less than delta, this set, which is contained in the first it has G disjoint, right? So we can have this and this set, this two set, a disjoint. And then once we have this disjoint, meaning what? Meaning like this one. Let's see. We can have this call this A, set A, which is depending on the delta and the Z, right? So this A, delta and the Z, this set is in intersection of this K, G is empty, so it must be in the M for all the x, f sub n of x minus f sub m of x, the absolute value less or equal than 1 over k, right? So if you take the complement, the G M K, the complement, right? The complement, this is a union, we have flip, so become intersection, and this is greater or equal than 1 over k, it become less or equal than 1 over k. So this set is a subset of this, right? So what does it mean? So that means like, therefore, if we write on this, therefore, if n is greater or equal than m, so we have f, replace, for every y is inside this. So if we replace x with y, so f sub n of y minus f sub m of y, take absolute value less or equal to 1 over k, right? For y with, the distance of y and z is less than delta, right? So look at this. For any y, if y is in this ball, right? So then f sub n of y minus f sub f sub m of y, take absolute value is less than 1 over k. Right? So we can let n goes to infinity, because for any m is fixed over here. So for any n greater than m, so if we let this goes to infinity, because f sub n converges to f, so then we have f n goes to infinity, f of y minus f sub m of y, take absolute value less or equal than 1 over k. For the k, we pick 1 over k less than epsilon over 2, right? So now we combine these two. So what do we have? So if n greater equal than m, then we we just estimate this f sub n of y minus f of y, the absolute value, and then we use the triangle inequality. So this is less than or equal to this, right? So we just insert the term f sub m of y, and then plus f m of y minus f of y, right? Take absolute value. So the first one, because of this inequality, less or equal than 1 over k. And then the second one, because of this, is also less than or equal to 1 over k. And this is less than epsilon, right? So what do we have? So we have for all epsilon greater than 0, we find a n, find some n, right? So when n, find m, and then when n greater than m, this f sub n minus f of y less than epsilon. So if we go back to the definition of converge subuniformly, so by the definition, of uniform convergency, this f sub n and this sequence converges sub uniformly at z, right? So when we have this delta and then have n, we have n and the delta, right? So for any y for which this the distance of y and z less than delta, this f sub n of y minus f of y, the absolute value less than epsilon. So by the definition, this converges at z. That means what? And then what is the definition of our E? E is the set of z at which f sub n does not converge subuniformly. So this means z is not in E, right? But z, so from z is not in G, we conclude that z is not in E. So therefore, E is a subset of G. So now we want to show, that G is meager. So this is our goal. G is meager. Once G is meager, E is meager. And F is a subset of E, so F is meager. So we're done, right? So now if you look at this, so now look at the definition of G sub mk. This actually we can write down in this format, like n greater or equal than m. And then this is just, f sub n of x minus f sub m of y, f sub m of x, taking absolute value. So if we define the function f sub n minus f sub m, take the absolute value, and then the pre-image of this, right, from 1 over k to infinity, this open interval, and then take the pre-image, it is the set, and then we take the union, it is actually a G sub m of k, right? So but this is continuous for any n and m, f sub n minus f sub m continue, and then this is open. So the pre-image of a continuous function of a open set is open. That's the by definition, right? So it's open. So G m sub k, G sub m k is open. This is open, right? So now see, since f sub n converges to f pointwise on x, that's by assumption, right? So which means for all x in the big X, this f sub n of x, this sequence is a Cauchy fundamental sequence, right? It's the fundamental sequence. It's called a Cauchy sequence. Therefore, we have this set. If we do the intersection m from 1 to infinity, g m sub k, this is exactly the intersection m from 1 to infinity, and then n, the union with n bigger than m, and then the set of x for which f sub n of x minus f sub m of x take absolute value greater than 1 over k. This must be empty. Therefore, this must be empty, right? Because if this is, because the reason is like if there is some x sub 0 in this set, m of x. If we write down, if there is x sub 0 in this set, it means what? It means like, it means that because intersection of OM, right? So for all m, and then x sub 0 must be in here. So there exists some m. For all OM, there exists some n greater than equal to m, right? Such that this f sub n of f x sub 0 minus f sub m of x sub 0 is greater than 1 over k, right? And then this cannot converge, right? So this s sub n of x sub 0, which means f sub n of x sub 0, this sequence is not Cauchy. Right? So it cannot be a fundamental sequence. So this whole set has to be the intersection of this open set G has to be empty. Now if we recall from problem 37, if you go back to problem 37, then the intersection m from 1 to infinity, the closure of this open set is meager for each k, right? So this is meager from problem 37. So therefore, so G is just the countable union of this, the closure of this, right, is also right? G, the definition. By our definition, G is the, so we have the open set. The intersection of this open set is meager, is empty, is empty. But now when we take the closure and take the intersection, it must be meager from problem 37, right? And now you have a countable union of this meager set is also meager. So G is meager, as we said before. E is a subset of G. So E is meager, and then F is meager. So we're done. That's it.